Yes.
Responsible for the MadFast similarity search tool, and his background is primarily a computer science and a software developer. Over to you, Gaba. Thank you.
I would like to welcome all, and I start sharing my screen. I guess my screen should be shared. Can you see my screen?
Not yet, Gaba.
Just a moment. And now?
Yes.
Okay, great. We can see your screen. Great. Please go ahead. Thank you.
Very good. Thank you. Thank you for the introduction. I would like to spend this short hour with talking about this tool of ours called the MadFast Similarity Search. This is a mainly in-memory search engine which is optimized for storing and similarity searching large molecule datasets, small molecule datasets. Large is meant here from any low number of molecules up to the over billion molecule ranges.
Where did you
So
go?
this tool can handle quite large datasets. A few words about the history of this tool. It's relatively young in Chemaxon's portfolio. It's launched in about 4 years ago. This tool has multiple interfaces. I will mention them in the later slides. And this is hopefully an evolving tool which will provide further functionalities in the future releases. You can find more information about the tool and about its documentation on the provided links. As the next steps, I would like to share some performance details on what raw performance can be expected from this tool on a server class machine. For this reference, I used an older Amazon EC2 instance, and the numbers mentioned here are for searching or handling 10 million structures. In this range, you can expect near linear scaling for performance. So, for example, if you want to search 1 billion structures, then you can multiply the times shown here by 100, or you can multiply by 100 the memory requirements mentioned here. So searching for a single query structure against a 1 kbit binary fingerprint talks on this mentioned Amazon RTC2 R3.80 machine talks around 50 milliseconds. For searching 10K query structures and fetching the most similar target from this 10 million hypothetical dataset can be run in 3 minutes, and after that you can use or post-process the results. In the end of this presentation, I will give an introduction on how such post-processing can be done. And for the memory and resource requirements, I would like to say that this hypothetical 10 million data set first should be pre-processed in 3 to 10 minutes, depending on the machine you are using. Around 1.3 gigabytes of disk space should be provided for pre-processed files. And after this pre-processing, nearly 10 seconds launch time by providing 2.5 gigabytes of memory for the in-memory storages, you have the ability to execute the searches mentioned before. I would like to mention that some public datasets will be available later for the participants prepared and used, and of course you have the possibility to use MadFast from the beginning and prepare your datasets. Let's talk about the interfaces this tool provides you. I would like to show a brief overview of the typical workflows which the users of MadFast encounter. Typically, a structure file containing molecules, for example, in slice format, is the starting point where one starts using this tool. And as I mentioned before, there are preparation steps where this molecular file is processed, fingerprints or descriptors are calculated, or even additional properties can be calculated. And the results of this pre-processing is stored in proprietary binary files. And these proprietary binary files are later loaded into memory by the MadFast embedded server, and the users can interact with this embedded server through command line applications, through REST API, or for some functionalities from a web UI from a browser. And of course, third-party clients can use the REST API, and there is the possibility, I will mention later, to use the underlying Java APIs to interact with the cores of MadFast. Let's talk about the web UI, the user interface which can be used from a browser. I will connect to a demo server here. This demo server will be different from what will be prepared for the participants, but the behavior is expected to be the same. So this page, what we can see here is the landing page of a demo server. And in the molecular descriptor section, we can see some data sets with various sizes and use various fingerprints to handle these data sets. For example, I can use the eMolecules Plus dataset, for example, prepared with chemical hash fingerprint. It's a Chemaxon proprietary liner fingerprint. This dataset in this version of the demo server contains a bit over 20 million structures. And on this interface, you have the possibility to draw query structures and see the most similar structures found in this dataset. And of course, it's possible to use chemical name to initialize the embedded drawer. You can edit the structure and you can examine and traverse the most similarities. Down here, you can see the distribution of all the structures, dissimilarities or distances in this target dataset. And here you can see the most similar structures along with an indication of dissimilarity or distance to the query molecule. It's possible to select molecules, and it's possible to change the dissimilarity metric, which is used for the searches for this display and for this display. So this user interface can be used to explore the chemical space of the download, the prepared dataset one by one, and you have the possibility to traverse this dataset and search what kind of structures are in it around the query structure. Let's go back to the presentation and to the interfaces. There is another user interface which is available in this embedded server. This is the real-time user interface for similarity-based overlap analysis results. I will demo this user interface in details a bit later after introducing you to the concept of similarity-based overlap analysis, or at least what is available in MadFast. And talking about interfaces, I would like to mention REST API is available, where you can interact with this MadFast server, and you can launch queries either from command line or from any programmatic REST API client. As an example, I will execute this query against a locally running MadFast server. Provided on my machine. I am sorry, but I run into a problem here. I will skip this. I would like to mention that you can find the REST API documentation on the web in the provided links, where you can see the description of each REST API endpoints and the parameterization of the REST requests. Let's continue the presentation. I would like to mention the command line interfaces, which are for preparing the molecule sets and calculate similarity-based overlaps. Details of the command line interfaces are also available on the documentation page. We have a list of command line interfaces and description. Here you can start getting familiar with the functionalities of these interfaces. And the MadFast distribution, the home of the MadFast tool, contains prepackaged self-contained examples which implement complete workflows for searching and preparations. You also can feel free to study these examples and getting familiar with the command line functionalities. And lastly, I would like to mention in the interfaces section the Java API provided by the MadFast tool. As I mentioned, this is a Java platform-based tool where various parts of the functionalities are available for Java API clients. And Java API API documentation is also available in the documentation package. You can explore it from the product documentation page. And we have examples on how to use these APIs. For example, on GitHub, you can see a complete project which outlines how to implement a custom fingerprint and inject it into the MadFast package and use it through all of the tools and all of the interfaces. And as a continuation, I would like to move on towards a more complicated topic. This is a kind of case study where we see how this tool can be used to characterize the diversity of a larger, over 1 million molecule-sized molecule library. For this characterization, we will use the similarity-based overlap analysis functionality of MadFast. A few words about similarity-based overlap analysis. This concept is around comparing two molecule sets against each other, or a single molecule set against itself. By comparison, I mean for every query molecule in the query dataset, in one of the datasets, we search for the most similar molecule in the target dataset. Here, in this mock example, we can see similarity scores. So in this small example, where we have 4 query molecules and 10 target molecules, we find that 3 query molecules have a close closing similarity score in the target dataset, and 1 is a bit farther away. And the result of this comparison can be illustrated, for example, in a histogram, where we bin the similarity scores or similarity values and see the distribution of the low and high values. In this example, we can say that for most of the query molecules, a close analog was found in the target set, and we can see it by the right-sidedness from this similarity score distribution histogram. I would like to mention that this use case, the similarity-based overlap analysis use case, was one of the foundational requirements which initiated the MadFast development. So this is quite a focus area for this tool. Let's move on towards the case study and see how can we use this functionality for diversity assessment. We will compare a query dataset against itself, used also as a target dataset. We will use MadFast for the overlap analysis calculations. And the result of this overlap analysis calculation is a preprocessed file, like the result of other calculations. And this preprocessed file can be examined in and post-processed in various ways. One post-processing involves an interactive user interface provided the MadFast tools, which I mentioned earlier. And another post-processing approach involves interacting with the Java API or the MadFast tools and interrogating this result file, this neighbors list, through a custom code. And this will be the other example of post-processing, which I will show you later. So let's move towards the interactive interrogation. I have an online demo for this. In this demo, on this demo server, we will see the result of a smaller analysis. This smaller analysis uses a random 1K subset of the PubChem database. This random subset is used as a query molecule set. And the target molecule set was the drug bank free database containing around 7,000 drugs and drug-like molecules. So we can expect that the random PubChem subset should contain some closed structures, and also we expect that it will contain quite diverse structures from the drug bank dataset. If you are interested in the details of these datasets, I recommend to check the MadFast documentation page mentioned a couple of times earlier. And there is a prepare public molecule sets part of this documentation, which contain references to all these mentioned datasets with home pages and script examples on how to acquire them and how to use them. So back to the interactive demonstration. What can we see in here? We can see this distribution histogram. This is now dissimilarity distribution or distance distribution histogram. We can see the various distances or dissimilarity scores we observed during this search, and we can see the occurrence count of these found dissimilarity values. Since it's a distance or dissimilarity value, then the close parts are on this side of the histogram. And as I've shown you, I can select on this user interface any part of this histogram. I selected this close part, and here on the lower part, we can see, just a moment, I will adjust the settings. We can see some of the selected query structure pairs. So these query molecules are molecules in the PubChem database. And next to each query molecule, we can see the most similar molecule found to this query molecule from the drug bank database. And as I move toward the dissimilar range, we can see that the most similar hits for these query molecules are getting more and more dissimilar. And this tool, this analysis searched not just one, but 10 of the most similar for each query molecules, and we can see them. So in this example, you can see the query molecules and the 10 most similar structures found for each query molecule selected here. And I can select the part of the queries or the results where only dissimilar structures found. And as I mentioned, I can select the similar range. And there is possibility to place further displays. And we can choose other properties or other parts of the informations for selection, for display and for selection. For example, here I will show the distribution of the 10th most similar target found for each query, along with the distribution of the most similar target. And we can use these two selections to select densely or sparsely populated areas of the chemical space of this overlap. For example, if I select this part where the 10 most similar structure is not similar, but the first most similar is similar, we can select the query molecules which fit into a sparsely populated area in the target set. And by selecting the similar part of the 10th most similar target dissimilarity distribution, we can select the queries which fit into the densely populated area of the target set. So these are the query molecules for which we have a lot of similar structures in the target data set. And it is possible to show the distribution of other properties which were considered during the preparation phase. For example, I can select the rotatable bond count from this list. Just a moment, I need to find it. So, for example, here we can select the flexible query molecules which hit into a densely populated area in the target set. So this user interface can be used for interactively interrogate the results of the overlap analysis. And as I mentioned about the documentation, you can see detailed examples on how to launch such overlap analysis on your dataset or on your results acquired from screening or any upstream tools. Let's go back to the presentation. I introduced you on how to interactively interrogate the results of an overlap analysis. And let's move towards a more advanced topic on how to programmatically interrogate this result set using the MadFast APIs. One might ask what this overlap analysis is good for. As I mentioned earlier, we aim to address the diversity of library in this example, but there are related workflows for which this approach can be adapted. For example, diverse structure sourcing task can be helped by this approach, or this approach can be used in a step where a large library should be, where a large library is reduced in size. It's also a valid approach to order a screening result library or a screening library into a diverse order, and it's also usable for more advanced analysis, for example, local hit rate analysis. All of these related workflows rely or can be used to the overlap analysis step as a data processing step. So let's move toward the offline programmatic assessment. As I mentioned earlier, the input data sets are processed by MadFast command line interfaces into a proprietary results file. I showed you during the web UI demo that this result file can be loaded into the REST server and exposed through REST API and through web UI. And in the next step, we will load it programmatically using MadFast APIs. And we will interact with the MadFast APIs through a JavaScript bridge provided by MadFast. And this JavaScript bridge will call into the MadFast Java APIs. And the processing steps and the information retrieval steps will be implemented in this JavaScript script. I will highlight the key concepts here, and the exact scripts will be made available upon request as an example. So the slide contains the launch step on how to launch this JavaScript bridge using a parameter describing the actual JavaScript file, which will be evaluated inside the JVM running MadFast. And as you can see, the actual JavaScript content is quite simple. We can directly refer to MadFast APIs, and we can instruct the MadFast APIs to load these files. These are just the highlights on the slide, and if I open the actual script, you can see that the related MadFast API, Java API locations are documented and can be looked upon. So after opening the result set of an overlap analysis, we can do interrogation programmatically. For example, we can answer clustering related questions. A valid question is, if I were to cluster the structure sets which were used for the overlap analysis calculation, how many outliers will I get if I use a specific cluster radius? And this interrogation step can be coded by literally a few lines of code. What does this mean? Typically, one might choose sphere exclusion clustering when the goal is to simply cluster a large data set. Sphere exclusion clustering simply select cluster centroids from the data set and assigns every structure which is in the close proximity of a cluster centroid to the actual centroid. And this close proximity is characterized by the cluster radius. Such functionality is available in the Chemaxon product portfolio. For example, the J cluster. So it is capable of running such clustering algorithms if you invoke it with your structures and your settings. So it will be covered in a later presentation. And we can see that there is a balance where we select such parameters as like the cluster radius, because if we select a too small radius, then we will cluster together the very similar structures only, and we will have a lot of structures which are singleton clusters, where the structure is a cluster centroid and no other structure is in its close proximity, like as shown in here. But if we select too large cluster radius, then we will see that a lot of maybe different structures are clustered together, and the clustering itself will lose its meaning. For this example, what's on the slide, the ChemBL dataset was used, and the execution of the ChemBL dataset was examined. And the fingerprint which was used can be characterized as a fingerprint where 0.25 dissimilarity is somewhat large dissimilarity radius. So one not necessarily want to move into larger cluster radiuses, because this is a threshold where you can expect that the clustering would lose its meaning. And we can see that in this case, from the Campbell dataset, around 60K structures will be outliers or singletons. And if we choose a bit more conservative cluster radius, which is still somewhat large, around a fifth of this dataset would be a singleton dataset. So this result illustrates that with very simple coding, you can get deep insight into the dissimilarity space of your dataset. And let's move toward the cluster size distribution assessment. One can use also a simple code to assess that what cluster sizes can be expected when a specific cluster radius is would be chosen. For example, if we choose a somewhat conservative cluster radius of 0.1, then the distribution of the cluster sizes can be seen here. And this says that, for example, in the Campbell dataset, which is a quite filtered dataset, apart from the more than 300K singleton structures, close to 100K clusters can be expected to contain only 2 structures. 60K clusters are expected to contain 3 structures, and so on. So we can conclude that if we would cluster the Campbell datasets, around 1 million structures would be scattered into 600K clusters containing 5 or less structures. And this information was derived from the overlap analysis result in itself. So as this example showed, that this overlap analysis functionality can be used as a valuable tool to characterize the chemical space of your library or your structural result set, and can help you to refine your workflow to further post-process your data set. The same results can be seen for somewhat larger cluster radius. So we can say that even with a large cluster radius, for example, for the Campbell dataset, we can expect over 200K clusters, which is considered the size of the dataset can be said that a too large cluster count. I would like to mention that in the customization possibilities of MadFast, there is an experimental feature which involves the customization of the front end of MadFast. These extension points are documented with examples, and these extension points allows you to reuse the real-time interactive UI components of the MadFast web UI to compose a custom user interface to your needs and to expose them through MadFast. This is a highly experimental feature, so if anyone wishes to experiment with it, apart from the documentation, we recommend to contact us and discuss the needs, and we are happy to help with advices and references. So that concludes my planned presentation, and I'm waiting for questions.
Oh, great. Thank you for that wonderful session. Now, let me see whether a few of the questions are there. And I apologize for the initial hiccups on the technical side, so that we had to move on to another live link. But I think now it's fine. So, moving forward, questions. I don't see much questions here, but yeah, I don't see much questions here. But if you can, personally, I have one thing to raise up. If you could give an idea, especially Surojit, how the participants of hackathon could give some access, how they could get access to this MadFast, and how they can get access to the software. So, if you can give some details about that, that would be great.
Hi, Giri. So this MadFast would be available on a predefined number of databases via the CDAC virtual tool room, which would be available from this week onwards. So we will already index a list of provided databases, or a list of databases that has been named to us. So those would be readily available and searchable.
Oh, great. So by that, so please participants, you will get access to this particular feature and the tool, as Surojit mentioned. You will get to know much more details during Friday at 2:30 p.m. During the presentation from Virtual Tool Room. So tomorrow we will be having a session from BioVia on flexible docking and binding energy calculations. And if you want to watch the previous sessions from Chemaxon, we have a playlist already in the MHRD Innovation channel. So I would like to thank all the members of DDH training team as well as the virtual tool room, including all the partners who are bringing up together solutions to hack the particular drug. And if you have any DDH20 registration queries, please route it to ddh at aict-india.org. Before we conclude, Surojit as well as Gabber, thank you so much. But if you have any concluding remarks on the MadFast and all the other techniques that you told today, you can please go ahead and give your concluding remarks, please.
Thank you, Giri. So our idea of providing the MadFast similarity search on the CDAC servers or the virtual tool room search access is that you would be able to search through millions and millions or even billions of molecules within seconds or instantaneously. So if you are wanting to work with large data sets, so that you will not have any limitations, be it the hardware or be it the software. So you can register and request access for the softwares. You will be able to access that, and we wish you all the best.
Thank you so much, Surajit, as well as to Gabber
Thank
again.
you.
And to all the participants, this is the official links for registration, the first one. And this is the email address, as I already mentioned, if you have any queries related to it. And the participants also will get access to like details on while you're registering, probably from this week, how to get access to these different tools. And so please wait for more details from the virtual tool room team. And the training sessions, all the training sessions are already in YouTube channel with different playlists. But if you have any more thing to know about details and do's and don'ts about the registration, please watch Dr. Abhay Jerry's YouTube channel. He has hosted two videos which gives you more details. So that's all from me for today. Thank you so much. Have a great evening. Bye.
Bye bye.
Thank you. Bye bye.